This is about some famous equations. Every so often something pops up on my computer screen, a video I could watch, and it catches my interest, so I click on it and give it a look. I've learned to stay away from eating contests of any kind, especially when they involve hot peppers. And lists are tempting, but usually not good either. But for some reason, when I saw 10 equations that changed the world, I got sucked in. I wanted to see them even though the video was nearly an hour long. I'm very impressed with equations as equations. The perfect balance of an equation is remarkable in itself. This, whatever it is absolutely equal to that, whatever it is. No matter how different they may appear to be, they are, in a sense, the exact same. They're equivalents. And I was wondering if any of these equations would be familiar to me. They should be. After all, they'd change the world. I was a little surprised when the person speaking in the video turned out to be a masculine mechanical voice. I guess you're going full-on nerd when you do that. The first equation was what we call the Pythagorean theorem, about the sides of a right triangle. Uniting Spencer, as I called the voice, said, geometry and algebra, and providing an accurate way of measuring distance. A squared plus B squared equals C squared. Boom. Next up was something about logarithms, invented by John Napier, improved by others, and a complete mystery to me. I think I might have seen this in high school, along with a slide ruler, just about the definition of old school, but I've mercifully forgotten it. Spencer was very impressed with logarithms. Differentiation, or the calculus, was next, discovered by either Leibniz or Newton or both. It's got something to do with approaching a limit without ever quite getting there. It's about infinity and splitting hairs. It's what's called the start of higher math, and it's one more thing I failed to understand while on my journey. I suspected others were about to come up. Newton's law of gravity is next. The force of attraction between bodies operating at a distance. Spooky. Still a mystery today, but that didn't stop Newton from quantifying it in an equation and declaring that it exists throughout the universe, common to all matter, which explained the orbits of the planets and so much else. Spencer was big on Newton, really revered him. Next up was a tie between something to do with imaginary numbers and Euler's formula for polyhedrons. I think the square root of -1 is an example of an imaginary number. Spencer said that Euler's formula has been called many times the most beautiful in all of mathematics. And Euler, whom I'd never heard of before this, is the greatest mathematician of all time. If you say so, Spence. The wave equation was next, measuring the vibration of a violin string and the height of a tsunami wave. Spencer said it was also useful in locating oil underground. The Fourier transformation was next, and I understood less about this than I had about what had come before, and that's really saying something, what you might call bountiful ignorance. Spence said it started with heat flow and was crucially important in the digital revolution, computers and cell phones. By this time, incidentally, I thought I was hearing a certain snotty or haughty tone in Spence's voice. I think he was making fun of me. One must know this in all of its full glory, he said, or not know it at all. Summarizing these equations, he said, some are extra easy and some can't be expressed in thought. No wonder I was lost. Next was the Napier-Stokes equation, important in aerodynamics and heart surgery. It is a means to understanding the flow of compressible fluids. Next is another tie, this one between Maxwell's equations for electromagnetism, jump-starting the world of electricity, built on the brilliant work of Faraday, and the Black-Scholes equation, an economic tool which led to financial derivatives, essentially creating virtual money, and the recent booms and crashes. Spencer called it a mess in the market. At the top, for Spencer, is another tie between Einstein's equation for general relativity, which goes beyond Newton to explain the workings of the universe, and Schrödinger's quantum mechanics, which explores the possibility of everything's existence at the subatomic level. Got that? All right, I would say that these equations may have changed the world, and Spencer made a good case for that, one by one, but they went right by me. It takes a certain kind of mind to observe the world, understand how it works, detect a pattern, and express that comprehension in a neat equation. E equals mc squared. Cool. I can't do it or understand it myself, but I can certainly admire those who do.